Assalamualaikum. Welcome, and I am going to explain to you the heat conduction experiment. So, in heat conduction experiment, you are going to validate the Fourier law, or you can say that you are going to apply Fourier law to calculate the thermal conductivity of a given material. Okay? As you know that the Fourier law is Q minus Ka dt dx. So, basically we will applying value the heat applied Q in watt and measure the temperature gradient. So, we have two cases, linear conduction and radial conduction. So, first let me explain to you the linear conduction. We will have a brass heating at one end. So, once you heat this one, the temperature will rise here and it will drop along the length of cylinder. And in experiment we have water circulation to take the heat out, so that a steady state profile is achieved. Okay? So, now you apply here heat and we will have a sensor along the length of the cylinder. It will measure the temperature at different positions. These positions of sensors are known, the value of x from the heat source. So, you measure T versus x, T1, T2, T3, T4 and so on, and then you will plot this graph. So, you get the slope will be the dt dx, the temperature gradient at a given value of Q. So, you can get the thermal conductivity, area of the cylinder is given, and for a given Q you calculate the dt dx. Okay. K can be calculated, or you can do different value, you can apply different value of heat and same measure dt dx for each cases. And here we are going to validate the Fourier law. So, you have different value of Q, you plot dt dx slope for each cases, and as we increase Q we expect that the slope will be more in negative side. So, you will have graph like this. If your this fit is linear, it means the applied heat is proportional to the temperature gradient, which is the statement of Fourier law. So, in this way you validate the Fourier law, and using this one Q proportional to dt dx, if you plot this one, the slope will be Ka, and this way you can calculate the thermal conductivity of material. It will be average value for all the cases. So, this is linear conduction. Now, let us come to the radial conduction. In the same setup we have radial and we have linear. So, this is good. What do? In the cylinder, in the radial conduction we have inner cylinder and outer cylinder. Heat is applied at the inner cylinder. So, once you have heat applied here, what will happen? The from axial side it is insulated. So, there is no heat conduction in axial direction. So, heat will be conducted in this direction. So, this is maximum temperature here. There will be temperature drop along the length along the radial position, and we have sensors at different positions. You measure the temperature at different radial position. In this case we do not expect profile to be linear, it will be logarithm. So, if you refer to the lab manual, you find this equation, derivation and detail are given there. So, here log term comes ln. So, profile will be non-linear logarithm, and using this profile, this equation you can get the thermal conductivity of material. So, temperature is maximum at this point and minimum as outer, and graph will be like this. So, this is the radial experiment, the profile is different, get the K. In the linear experiment we have dt dx will be linear along the length of the position, and you get Q by applying Fourier law. Okay? So, we will go to the setup now. That is it for now. Thank you. I am going to show you how to conduct heat conduction experiment. So, this is the bar here, you can see, and we are hitting the bar at this side. So, Q is applied here and applied Q is 87 watt right now, you can see. So we are heating at this point, and then the cooling arrangement is there. We are taking water from the tap, and cooling is going through this to take the heat out, so that once we apply heat here, the temperature is built and the steady state profile is achieved. Okay. So now we are heating at this point. We have sensors 1, 2, 3, 4, 5, 6, 7, and this is the middle material. So we measure temperature along the length of the cylinder. So you can see the temperature here, T1, T2, T3, up to, we have nine sensors here. Temperature is dropping, maximum is 104 and up to 41. So we can see, you can see the profile in the gradient in different region. Still steady state is not achieved, almost achieved. You can see the slope in this region is 0.71, here 0.73, 0.71. So almost the slope is coming close to each other. So a steady state profile, we expect that it will be linear with the same slope. So for this, as a given value of Q, you find the dt dx, and then you can calculate the thermal conductivity. Also here we have a radial line in the same connection. So in radial conduction, what we have inner cylinder here. You can't see, I'm sorry. You can this is here we have heating the inner one, and then insulated in the axial direction, you can see, and then heat will be conducted along this radial line. So once you heat in inner cylinder, heat will be conducted along the radial position, and we have sensors T1, T2, T3, T4, T5, T6, and that you will measure those values and you get the profile and apply the equation I shown to you. The one is for radial conduction, and here we can see the data for radial one, circular discs. And you can see we have 6 sensors here. Profile is logarithm or exponential. So this profile you will use for radial conduction to calculate the thermal conductivity of material. Okay. So here also you can see the temperature is dropping, but the nature is not linear. So you can see this, you will fit a logarithm curve graph to get the thermal conductivity in the case of radial conduction. Okay. You have the data and you can proceed for the calculations. Thank you.